Hello, we are back with another video tutorial. This time this is another buffer problem. Now the problem is telling us that a buffer solution contains 10.0 grams pyridine with a general formula C5H5N and 15.0 grams of its conjugate acid per 1 liter of the solution. The first question is, what is the pH of the solution if the Kb, or the basicity constant, if you can remember that in your basic acid-base chemistry, of the pyridine is equal to 1.40 times 10 to negative 9. Okay, so that is the first question of this problem. So to start in solving this problem, we have to look at the given. We're only given the amount of our species in our solution. That is 10 grams of pyridine and 15.0 grams of its conjugate acid, and the Kb of the pyridine. So we have to take note that the grams should be converted into moles. Then the number of moles should then be used to calculate for the molarity, which will then be the concentration of our species in the solution. So let's start with that. Alright, so first calculate for the number of moles of our pyridine. So we have 10 grams of pyridine, then we try to use the molar mass of pyridine. Now if you forgot how to calculate for the molar mass of pyridine, you have to remember that you simply try to sum up all the atomic masses of the individual elements present in that formula. For example, we have C5H5N, so you have to multiply the atomic mass of carbon with 5 because you have 5 carbons there. Then you do the same for hydrogen, then plus the atomic mass of your nitrogen. So you will get 79.09 grams. Okay. Then when you do the calculation, you will have 0.126 moles. So that is the number of moles of your pyridine in the solution. Then we calculate for the next the number of moles of your conjugate acid. Alright, so for the number of moles of your conjugate acid, we have 15 grams of the acid times its molar mass, of course, as I've mentioned earlier. So you simply add one additional hydrogen, so that becomes 80.09 grams per mole of the said conjugate acid. So when you do the calculation, you will arrive to 0.187 moles. Now you now have the moles of your pyridine, which is the base, and the moles of the conjugate acid. Now all we need to do is divide by the total volume, which is 1 liter, for us to convert the number of moles to the concentration, which is in the unit of your molarity. So let's do that. So we simply divide the number of moles of our pyridine with the total volume, which is 1.0 liter, and that is 0.126 divided by 1.0 liter is equal to 0.126 moles per liter, or abbreviated as capital M. Remember, capital M is the symbol for your molarity, which is the unit of your concentration and is usually used in your buffer solution problems. Okay, let's do the same for your conjugate acid. And there you have it. This is the number of moles, the molarity of your conjugate acid. So you have here the number of moles earlier we calculated, 0.187 divided by the volume, which is 1.0 liter. So the molarity, or the concentration of your conjugate acid, is 0.187. So we now have the concentrations of our species in the solution. So the next step would be to determine the equation of the equilibrium. Okay, so we like to write the equation that it will be our guide to see the species before and after the reaction. Let's do that. Okay, so simply the equilibrium equation for this solution is shown here. Okay, so this represents your equilibrium arrow. So you have here your base, your pyridine, dissolved in water, and in the solution it will form the conjugate acid, this one, and of course the OH minus, hydroxide anion. So for us to solve this problem here, we have to use the ice chart. Now what is the ice chart? It involves the I for the initial, C for the change, and E for the equilibrium. So we'll be trying to identify the amounts, okay, of the species present initially, after the change, and during the equilibrium. So let's do that. Okay, so we start with the initial. So initially we have 0.126. Now remember, we will be using the molarity, or the molar concentration of our species in this ice chart. Okay, so you must take note of that. So for the pyridine, we have 0.126. We start with that. Then our conjugate acid is 0.187. Of course, the base here, the hydroxide anion will then be 0. We will not be taking note of water because that was just the solvent in the solution, and later on in the equilibrium equation it will not be also used. Okay, so this is then followed by your change. Now for the change, of course, this will be used up in the reaction. So we have negative x. The x here will then represent the change. So for the conjugate acid, of course, it will be formed, so that's plus x, and also for your hydroxide and ion. Then the next will be at equilibrium. So basically, at equilibrium, the concentration of your pyridine will be 0.126 minus the change is x, so that's 0.126 minus x. For your pyridine, that's 0.187 plus x, which is the change, so that's the additional. Then of course for hydroxide and ion, that's simply the x, because 0 plus x is simply your x. So this is an example of your ice chart, and this is very useful in solving your buffer problems. This is one of the ways in solving your buffer problem, aside from your Henderson-Hasselbalch equation. So what will be our next step? So the next step is to identify the equilibrium equation and plug in the corresponding values. Alright, so our equilibrium equation for this equilibrium here that is being described, it's shown in this equation. Okay, so we have the conjugate acid, the concentration of the conjugate acid times the concentration of the hydroxide and ion divided by the concentration of your pyridine. So let me just complete the equation there. Alright, so always usually the bracket symbol determines or signifies the concentration in molarity in this type of problems. Okay, so if you don't remember how do we arrive to such equation, then you need to have a little review on your writing your equilibrium equations. But the important thing there is you always have to remember that looking at your equilibrium here, you always have your products over your reactants. So your products are here, so that's why you found them here on top on your numerator. Then in your denominator are your reactants. Now remember, we in an equilibrium equation, we do not include pure liquids or pure solids for that matter, or any substance in its pure form. So that's why you don't see water here in the equation. Okay. Then of course we have Kb, which was given in the problem. So the next step will then be to simply plug in the values as we have already determined here in the ice chart. So let's do that. Alright, so we now have plugged in the values. You have here 0.187 plus x, that is the concentration of your conjugate acid, multiplied by the concentration. Now remember, this is at equilibrium. The concentration of your hydroxide and ion, which is x, which is the change, then divided by the concentration of your pyridine, which is 0.126 minus x. Now another interesting thing that you need to always remember in solving buffer problems is that usually the x, or the change, is negligible in terms of its value. So that simplifies the whole calculation, because otherwise if that is really on a higher value, that will transform the whole equation to a quadratic equation, which will then take a longer time, if not a very hard time for us to solve the problem. So we do that, and taking note that the x here, the plus x minus x, will just simply cancel out because it is negligible as compared to the concentration 0.187 or 0.126. So let's do that. Alright, so we now plug in the values. Kb is equal to 1.40 times 10 to the negative 9. Then we now have cancel out the plus x minus x, as we have said earlier, that is negligible as compared to the value 0.187 or 0.126 as the concentrations of your species. We're only left with the x, which is generally the whole change in the equilibrium. So a simple algebra will then be used for the next part, because you have to solve for x. Okay, so to do that, so we simply rearrange this equation here, and we arrive to this equation, 0.187x is equal to 1.40 times 10 to the negative 9 multiplied to 0.126. This is the concentration of your pyridine. Okay, so we solve for x, and the x is equal to 9.43 times 10 to the negative 10. And remember that x is the concentration of our hydroxide and ion, which is the change. So from there, we now have the concentration of the hydroxide and ion. We can now calculate for the pOH, because pOH is simply the negative logarithm of the OH minus concentration. So let's do that. Alright, so we now simply plug in the values. So pOH is negative logarithm of the hydroxide and ion concentration, so that's the negative logarithm of 9.43 times 10 to the negative 10. So we do the calculation in your calculator, of course. Now, if you have a problem in using your calculator in terms of the logarithm, you have to review on that as well. So the POH is equal to 9.03. Okay, so the number of mantises here determine the number of significant figures. So that's why you have 2 mantises here. You only have 2 as well in your final answer, which is 9.03. But wait, if we look back at our question, the question was calculate for the pH of the solution. So we go back here, we arrived at our POH, so we simply use a common equation that was mentioned or introduced in the previous video that we had, which is pH plus POH is equal to 14.0. Okay, so from this equation here, we then calculate for the pH, and that is equal to, alright, so that is equal to 4.98. So that is, the pH is equal to 14.00 minus 9.03, which is the POH, and that is equal to 4.98. So the pH of this given buffer solution that was described earlier is equal to 14.98. So that is the final answer. Thank you for listening and continue learning.